for inviting me. So yeah, as the title says, I will be talking about Lovasz theta function, semi-definite programs and algorithms. I expect that the audience would not have seen any of this before, including the algorithms part specifically. So what I will do is I will hopefully define all the terms and go at a slower pace so that you can kind of grasp the key ideas in this, very beautiful subtopic. Okay. And please feel free to stop me at any stage if you have questions and let me know. I'll be happy to answer any questions. Okay. We have enough time through 4 lectures to cover all the main ideas in this. Okay. Good. So the talk or the series of lectures that's my part will basically be connecting um, two very prominent figures in their respective fields and across fields actually. Claude Shannon from information theory, Laszlo Lovasz from combinatorics, discrete mathematics primarily, amongst other fields. And this beautiful interplay between graphs and high dimensional geometry. Okay, and the connection that was discovered. And the work that we'll see today is particularly, and I'll mention it again, is particularly very interesting because it was in some sense far ahead of its time. So the work that we'll be discussing primarily for the first 2 lectures is going to be based on some papers from around the 1950s and the 1970s. And these ideas turned out to have far more wide-reaching applications. They were ahead of their time, or rather extensions that are now very much a part of CS algorithm design. Okay. But so today's outline is going to be basically the following. I'm going to motivate optimization problems in computer science, especially with respect to graphs. Okay, I think if you're a mathematician, you might be interested in structural properties of graphs, whereas from a computer science perspective, we are also interested in how these can be computed fast, right? Or certain computational problems related to these structures on graphs, right? So we'll be talking about the optimization aspect. I'll try to motivate that. And then we'll go to these definitions of what is a Shannon capacity, the theta function that was in the title. And we'll hopefully stop at by covering some important connections whose theorems I'll be able to prove tomorrow likely. Okay. So this for parts 3 and 4, which will be tomorrow. So we'll come to that later. Good. So let me start with a very practical sounding problem, okay, which is the following. Uh, you have multiple telecom towers to be set out in a city, right? And 2 towers are going to conflict if their signals interferes when they use the same frequency. Okay. So for instance, you may want that towers that are close by should for some reason use different frequencies, right? Okay. So now the question is, once you have this layout of towers, the telecom company wants to determine that which towers can broadcast simultaneously on the same channel. Okay. So clearly, since these three towers seem to be drawn close to each other, they should use different frequencies. Maybe one that is quite far apart can use the same frequency as one of these towers and still broadcast without interference. Okay. So this is the question. It's framed slightly vaguely, possibly, but could someone attempt to come up with a mathematical description of this related to graphs and how one might model these as a graph problem? So I think you have seen certain graph questions previously in this series. So is there any graph question you can think of that would model this problem? Okay. So maybe you can leave your answer in the chat or feel free to just speak it out aloud. So I'll give you a minute to just think about this. But if there are questions in the chat, yeah, I should be able to see them. So if you type in your ideas on the chat also, I can kind of comment on how it works. But okay, so here's one possible way to model this problem as a graph. Okay, Right. So here's one possible way to model this as a graph. So put the towers. So you build a graph with vertices and edges, okay, where the towers represent vertices. Or rather, I should say the vertices represent the corresponding towers, right? And the edges, there's an edge between two towers. So I'll call the towers I and J. If what happens? Well, you have tower I, tower J. If for some reason they would conflict if they broadcast on the same frequency, like in a previous example, suppose they are close to each other, right? Then they may conflict if they transmit on the same frequency. So put an edge between them. Okay. So you build this graph of all towers. Right? And now what do you want in this graph? Can someone tell me what is the quantity that I want in this graph? If you want to find a set of towers that can transmit without conflicts.
So those who are connected should have different frequencies.
Right. Okay.
Um,
So those who are connected should have different frequencies. Now, the question is basically that, how many of them can simultaneously use the same frequency? So that's the question. So just a way to rephrase your answer to this is going to be basically that if you have, um, for instance, this J and K in what I've drawn should be able to transmit because they are not conflicting. So they should be able to transmit on the same frequency. Right? So there are two towers in this particular graph that I have drawn that can transmit at the same frequency. Can someone find a bigger one? Can there be three? So let me label these vertices. I'll remove the I and J. Maybe I'll label it as 1, 2, 3, 4, 5, and 6. Right?
154.
Exactly. So 1, 5, and 4 can transmit at the same frequency without any conflicts. Right? Because there's no edge between any pair of them. So they can simultaneously transmit on the same frequency. Right? Can someone find a bigger one, bigger set? Like, are there a set of four vertices or four towers in this layout that can transmit at the same frequency? Well, looks like not, at least in this one that I've drawn. Okay. So for instance, over here, what we are finding is basically a subset of vertices such that for all I, j, and s, you take any pair I, comma, j, and s, they don't have an edge between them. Right? So the set 145 does not have an edge between them. And what is this called? You might have seen this quantity before. Yes, exactly. So it's an independent set in the graph. Okay, and what you want is the maximum independent set. So such a set is called an independent set. And what we are asking for here when we ask this problem is what is the size of the maximum independent set in this graph?
But why maximum? Why not minimum? I mean, if you are trying to set. Uh,
Mhm. Yeah, okay, good question. So why not minimum, right? So what is the minimum sized independent set in this graph? Right? You can take a single vertex and it by itself is an independent set because it can transmit alone on a frequency. Right? Whereas what you want to do is you want to maximize how much information you transmit. So if 4 towers are transmitting information at the same frequency, you're using less resource. That is, you're using only one frequency band and managing to get more information across. Right? So that is the motivation for looking at the maximum independent set. Is that clear?
Okay, yes, sir.
So this is the quantity that we're interested in. So you can see that this naturally models as a graph problem, which is called an independent set. Okay, the word independent, if you have not heard it before, is because there are no conflicts between any pair of them. Okay. So here's another seemingly unrelated problem or application that's also I'm formulating as a graph problem. Okay, so you've got a high performance computing cluster. The word doesn't matter. It's just that you have a set of tasks and a set of machines. Okay, so here are my tasks. So let me label the tasks. Okay. Now, when you want to access a high performance cluster and perform certain computations on them to accomplish a task, two tasks may require the same resource. Okay. So some pairs of tasks among these cannot be run at the same time because they require the same resource. Maybe they require a very specific processor or a configuration, and there's only one of it that is available. Right. So now you want to figure out the largest batch of tasks that can run in parallel without any conflicts. Okay. And quite simply, you can again see that this is just a case or an example of a maximum independent set, right? How? Again, there's a modeling problem. You have vertices 1 to 6 representing the tasks, and you put an edge between two tasks I, comma j if they conflict, right? And so now you build this conflict graph, so to say. Maybe 3 does not conflict with anything at all. It has its own set that it can run on, right? And now, if you find the maximum independent set in this graph, you would exactly answer the question that is asked over here. So this just goes to show that in case you're unfamiliar with these computational problems, that first of all, finding the maximum independent set is kind of a fairly natural, practical question that may turn up in various settings. And in fact, it turns up in these two unrelated sounding settings, but basically underlying it is the same problem, right? Good. Any questions about this? Okay. Again, the goal is to find the maximum independent set. Good. Okay. Let's go on to a slightly different problem. Okay. So here, a professor has to schedule n exams. Okay. And two exams cannot be scheduled in the same slot if some student has registered for both of the courses. Right. And now you want to minimize the number of days, right, in which you can schedule the exam. Uh, So one question is, of course, if you ask the maximum number of exams that can be scheduled simultaneously in the same slot, what does this become? Okay. I claim that this is again just a case of the maximum independent set problem. Okay. Again, two exams will conflict if some student has registered for both of them. So you could possibly just construct this graph, feed it into a computational thing, and find. Suppose I ask the slightly related question, which would be asked in the previous ones also. What is the minimum number of days required to schedule all of them? Okay. I hope you can see the bottom of my screen where I've written the word exams. It doesn't seem to be turning up in the preview, but
Yeah, it is visible. Yeah.
it's visible. Okay, thanks. Thanks, Rajesh. Yeah. Good. So what's the minimum number of days required to schedule all the exam? Okay. Again, I claim that this is slightly different from the maximum independent set problem that you have seen. Right? Why? Let's try to model this first and see how, but it's quite closely related in them. So we build a graph where vertices. So I'll call this graph G the conflict graph. Okay, the vertices V represent the exams that are to be scheduled. Okay, and you have an edge as before. If the exams I comma j conflict. Okay, that there's some reason of conflict. For instance, the same student has registered for both courses. Okay, so now that you have this, what I want to ask, what I'm asking is a slightly different question. What is the minimum number of days required? Right? And if you draw the conflict graph as before, let me say this instance. Okay, so suppose this is the conflict graph that I've drawn out of it. If I pick out a maximum independent set in this conflict graph, it gives me a set of exams that can be scheduled in the same slot. But I'm asking for the minimum number of days that are required. Right? So can someone relate this to a slightly reformulate the problem and tell me how this can be done?
Maybe some of the maximum independent sets which can cover all the nodes.
Good. That's a good starting point. The idea is you pick out an independent set, schedule it on one day. You pick out another independent set in the remaining graph and schedule it on the next day, and so on. That makes complete sense, and the answer is very close to that. Except that may not always work. So here's what I will say. What I will do is think of each day as a color. Okay, so maybe I have three colors here, red, green, and blue with me, right? Now I'll try to color the nodes or the exams or assign colors to these vertices, which basically means assign exams to days so that, so suppose I color that exam 1 is held on day number red, okay, which is maybe Monday, right? Now, what exams can I not hold on Monday then? Right? Clearly, I cannot hold 2 and 6 on a Monday. Okay, if red is a Monday. So this is right. Then maybe I say, well, okay, I cannot hold 2 and 6, but I will try. And this is exactly the algorithm that is described. I'm heuristically following that. Maybe I'll hold 4 on a Monday. Right. Now, is there any other exam that I can hold on a Monday on the same day? Well, I can hold 7. Now, that's all that I can hold on the same day because every other thing conflicts with the Monday exams that are already scheduled. I can hold 2 on green, right? Exam number 2 on, say, Tuesday. Maybe exam number 5 on Tuesday. Okay. And I can also hold exam number 3 on Tuesday. And finally, 6 I have to schedule separately. So I will do it on a separate. So 6 is a Wednesday. Okay. So I've scheduled all the exams on 3 days following exactly the heuristic that has been suggested. Okay. Disjoint independent sets that cover the graph. Right. Good. So can someone tell me what I've done exactly here? Does someone know a term for this already in the graph literature? Coloring problem? Exactly. So this is an example of a graph coloring problem. It's closely related to the independent set problem. Oops, sorry. Yeah. So what we are doing basically is assigning colors to node. It's just a different way of looking at what was suggested, such that no two adjacent nodes, when I say adjacent, I of course mean they are connected by an edge, have the same color. Okay. We'll define this formally in a moment, but then what we want to do is assign colors to node while minimizing the number of colors. Okay. And this minimizing is what gives us the minimum number of days that are required. Now, can someone tell me why this particular conflict graph that I've drawn here will require at least three colors?
Because there is the complete graph of three.
Exactly. So there's a complete graph. Exactly. There's a triangle sitting here, 1, 2, 6. It is a complete graph on three vertices, and therefore that complete graph has to use three colors at least. Right? For instance, we could have used maybe 7 colors and given every vertex a different color, but that's somewhat wasteful, right? So typically in computer science problems, we are looking to figure out what is this minimum coloring that is required in a computational way. Okay, and that's where the computer science motivation for this comes. In structural graph theory, one could prove results about coloring, the existence of colorings in certain graphs with structures and all. And in the optimization perspective, we are looking to find such a coloring because it's useful maybe in some practical applications. Okay. Good. So given the above, we have defined basically two quantities. We have defined what an independent set is, what is a coloring. Let me just define it again over here. For concreteness, it's a subset of vertices such that an independent set for any pair of vertices. In fact, let me just assume that it's a simple graph, no self loops. Okay, and this is the size of the maximum independent set. Typically, the size of the maximum independent set, I'm going to denote throughout this series of lectures by alpha of G. This is standard notation. Okay, good. So for instance, here's a graph. As your graph gets more complicated, you can figure out that, finding the maximum independent set becomes more and more complicated. Can someone suggest a very brute force algorithm or brute force process to find the maximum independent set? What would be a trivial kind of way to go about finding, given a graph to find the maximum independent set in it? So I should be careful. You can have multiple maximum independent sets. So what would be one way to find a maximum independent set in the graph? Any suggestions? So, well, let me just tell it, the brute force way is just to go over all possible subsets of vertices, right? And how many subsets of vertices are there? There are 2 raised to n subsets of vertices, and that's like exponential. So just go over all subsets, check whether they are independent. Okay, and out of them, output the one with the maximum cardinality, any one with the maximum cardinality. Okay. Can someone suggest slightly better algorithms for this? I should be careful. I have not mentioned this, but the size of the vertex set is n, which is why I'm saying 2 raised to n. There are 2 raised to n subsets. Maybe you want non-empty subsets, so 2 raised to n minus 1. But as I've seen in asymptotic analysis, we don't care whether it's 2 raised to n or 2 raised to n minus 1. So can someone suggest a slightly better algorithm than this or procedure than this to find a maximum independent set? Well, maybe you could try some things like, start at the, start with set of size n, check whether it's independent, then go down below, check whether it's independent, and so on. So maybe that saves you some amount. But in the worst case, it doesn't really save you much, right? You want one procedure that works for all graphs that could come as input. So keep this in mind. We'll come back to this sometime later, this question of whether you can do a better than this algorithm. Okay. So what is the chromatic number? Well, the chromatic number which is denoted as chi of g, is dependent on what is called a proper coloring of a graph. So what is a proper coloring? A proper coloring is a function from the vertex set to some integer k. This is called a proper k coloring. Let me just write it. For all edges, I have chi of I is not equal to chi of j. So chi is the typical term used for coloring. So you're assigning colors to every vertex, and you want that no adjacent vertices receive the same color. For instance, here is the famous, here it's a quite famous graph, and the chromatic number of this, as you see, is what? Is 3, right? Because you've got red, blue, and green. Or at least, sorry, let me not say, there's a proper coloring shown over here. Right? And based on proper colorings, the chromatic number chi of g is the minimum number such that g has a proper k coloring. Okay, and just like the previous alpha of g, finding chi of g is an important problem in computationally. Okay, now let me give you the bad news. Okay, so you thought of some time about coming up with better algorithms. Turns out that you can show that you really cannot come up with better algorithms than 2 raised to n. Okay. So both alpha of g and chi of g, remember alpha of g is the maximum independent set in a graph G. Chi of g is a chromatic number of the graph. And both of these are really hard to compute, or at least are believed to be hard to compute. Does anyone know why I'm writing believed to be hard to compute? So maybe a poll, or you can raise your hand or something. So how many of you are aware of the P versus NP problem, or have at least heard of it? So so P versus NP is basically a fundamental question in computer science about the nature of computation. Whether certain problems can have efficient algorithms. And it's widely believed that alpha of G and chi of G fall in this class of problems that are called NP hard. And they're called for a reason that people have tried for many times, and they have good reason to possibly suspect that you cannot have efficient algorithms to compute it. Okay, so you might have seen things like either minimum spanning tree, or doing a DFS or BFS on a graph, or finding shortest paths in a graph. Right, these are problems on graph you have seen. Even maybe max flow and min cut to be more non-trivial if you have seen it. So these are problems on graphs that have efficient algorithms. Okay, that means the running time of these algorithms is something like polynomial in the input size, right? Polynomial in, say, the number of vertices n. Whereas for alpha of g and chi of g, they are only expected to have exponential algorithms. Okay. So if p not equal to np, alpha of g and chi of g, I'm just writing this. If you're not aware of p and np, that's fine. Now you can just see that this is kind of the core thing that one can take as a standard, as an assumption. And if one proves this, it's a really huge thing. Can't be computed in polynomial time. So what do I mean by polynomial time? In case you're not aware, it's just like running times like n squared or n cubed or so on. Okay. Or say an order n raised to 100. So what is expected is that you remember the brute force algorithm I'd shown you for independent set is expected that it'll take that much time. Good. But they turn up frequently in practical applications. You've just seen like 3 or 4 examples, and now given those, you can dream up maybe 100 more where some version of the independent set or the chromatic number will turn up. Right? And so what do? You can't just give up and say that I will not compute these quantities. Right? So what one typically does is look for approximations to these quantities. So given an input graph G, maybe you cannot tell me what is the size of the independent set because the graph has like 1 million nodes and I cannot run my brute force algorithm, right? So, but then you say, well, okay, I cannot do this trivial algorithm because it's too costly for me computationally, but I will do something quicker that may not give me the maximum independent set, but it will give me a solution that is close to the maximum independent set. Oops. So here's the kind of fix, so to say, or the idea for the fix is to approximate the solution. Okay. So what do I mean by approximate? This is a really interesting thing that we'll come back to in a moment, maybe come back to after maybe in the end, towards the end of the second lecture or tomorrow. That when I say approximate the solution, what I mean is actually give a mathematical guarantee that the procedure that I do produces an independent set that is close in size to the maximum independence. Okay, so for instance, when say n is equal to 1 million, yeah, this is 10 lakh, right? Yeah. So when n is equal to 10 lakh, if alpha of g is say 10,000, okay, then I will not give you an independent set of size 10,000, right? But I can output a set S, which is independent, and size of S is like at least maybe alpha of g by 2 or something, right? So instead of 10,000, I'll give you an independent set size of maybe 5,000, okay? And typically in applications, this may be good enough because you may not get the optimum, but you're getting, relatively close to it, right? So this is the notion of an approximation algorithm, okay? Now, unfortunately, the bad news is that both alpha of g and chi of g are really hard. I mean, they are one of the hardest problems computationally. In particular, to compute the maximum independent set, you know, you cannot come up with anything close to even like a half approximation, as this is called over here. Okay, and I will maybe give more details on it when we come to the approximation part of these 4 lectures. But for now, you can remind that this is a valid goal to strive towards to give an approximate solution. But in some cases, even giving an approximate solution may be hard, but we will try to do the best that we can. okay, all the time while maintaining efficiency of my algorithm. Okay, good. So I wanted to introduce this algorithmic viewpoint. Before, we'll put the algorithmic viewpoint on hold for a while, right? And kind of go to a slightly different problem, again, which we'll model using graphs and which will be the main subject of the next two lectures of this and the next. Right? Yeah, and this relates to information transmission. Okay. So you're familiar with, we exchange information all the time. I mean, this current information that is coming to you online is via some sort of a channel, in fact, multiple channels. Okay. So let's take the simplest model. Okay. So suppose you want to send kind of a message to someone over a noisy channel. Okay. However, there's an issue with the channel. It's not perfect. Okay. For instance, maybe due to real life, um, interference or otherwise, whatever the electrical uh, interference might be there, certain symbols may be corrupted in transmission, and when it is received at the end, it may be misread as others. Okay. So this kind of, already models a similar conflict, similar to what you've seen before. Okay. So take the following simple example, and this is quite instructive. We'll come back to this soon enough. We have a communication channel with 5 possible symbols. Okay, just 5. It's not this A to Z or even more. There are lots of symbols. Let's just take the simple case of 5 symbols to be transmitted across a channel. But now maybe adjacent alphabets can get corrupted. Okay, so for instance, what does this mean? If I have an A, right? So let me take, these are the 5 input alphabets. I'm drawing a slightly different graph here. We'll come to a conflict graph soon. But across the channel, when you send it, so this is my input symbols. What is my output symbol going to be, right? Turns out that your channel is such that A, think of these A, B, C, D, E as being cyclic, mod 6 or something symbols. So A can either, so here's my output symbols. So A may turn up either as A without corruption, or as B, or as E. Okay. B might turn up as either A or B or C. C might turn up as C or D or B. Sorry. Okay. So A can be confused with B and E. I've just summarized this. C can be confused with B and D, and E with A and D. If you send A and you receive A, that's fine. But suppose you receive a B, right? You don't know what was the input symbol that led to this B, right? For instance, it could have been either A, it could have been B itself, or it could have been C, right? So the distinct letters that lead to the same thing are basically conflicted, same output symbol. And the goal is the following. You want to transmit a message without confusion at the decoding end. Okay, I'm just calling it decoding end. Think of it as the output end. There's no real decoding process here. Okay. So now, if you want this to happen, at most, how many alphabets among A, B, C, D, E can you hope to send? Okay. So you could do the same modeling as before, right? You could say that if I send A conflicts with B and E, okay, B clearly conflicts or has a confusion with both A. I didn't write B with A, but yeah, that's just the confusion. Okay. So this is the conflict graph for the symbol. Very similar to what we have built before, right? Different letters that may be mapped to the same letter. Okay. Now, how many of these can I hope to send across at max so that there's no confusion? So this is a 5 cycle, right? And you can pick a maximum independent set in this and send it across, and that will not be confused. Right? So for instance, a certain maximum, you can take the multiple, but A and C. Oh, sorry. Okay. So a maximum independent set in this, if sent across, will not be conflicted. Right. So let us try to build another example just to make this more clear. Right. So here's another example. It's not a cycle. That's why I give it. E can go to E and F can go to F, I can go to I, J can go to I and J, L can go to I and L. Okay. So now based on this, if you build a conflict graph, what does it look like? So for instance, suppose you receive, let me be careful, JILL, right? What were the inputs that could lead to this? Right? Can someone suggest 2 or 3 words that could have led to the output being JILL given this graph?
One would be JILL, then JJLL. I mean, instead of I, we can have the
Yeah, so
also
for
put
instance, you could also have exactly, you could have JJ, LL and so, right? So this could be one thing, right? So there are multiple things that could lead to it. And therefore, if you draw the conflict graph that is directed here, if you do an independent set in this graph, it will not cause confusion. So that's kind of the idea. Okay. So what about JLLL? Is that a confusing thing? So I got JLLL. So J could have arisen from J. L could have arisen from only L. So yeah. So JLLL will not arise in the output, right? If I send JILL, if I receive JIL. Yeah. Okay. So if you go to like in electrical engineering information, there more general forms of corruption are studied over stochastic channels. But for our case, we will look at just this type of corruption, okay, which is basically confusability. Which two can be confused amongst each other? Okay. So for instance, E and F are confusing to the output receiver because he doesn't know which it has come from. Right. Similarly, I, J, and L are conflicted because if you receive one of these, you don't know where it came from. Right? So that's the idea. Once you build a conflict graph, the question is what is the maximum you can send across the channel? And you can say that if I send an independent set across, then there'll be no confusion. So for instance, the input and output agree, for instance, that the only symbols that the input person is going to send across is E, let me, is E and I, right? Or maybe even E and J. If these are the only two that they decide to exchange at all throughout the process, then it's clear that, basically there's going to be no confusion. They decide on this beforehand. Even if the channel corrupts J to I, that's completely fine, right? Because if the possible outputs that you may receive while sending E are E and F, but that doesn't conflict with J at all. Okay, so there's no confusion between E and J. So you can send two symbols. So basically, you can send two possible messages using a single alphabet. Okay. But now you can ask the question a bit more. Suppose I want to do something a bit more involved, right? So in both these cases, I could send only kind of two alphabets at a time. Uh, Maybe this graph may be a bit incorrect. So yeah, you should ignore this and just look at the conflict graph. We'll clarify it a bit later. Yeah. So now what if you're allowed to transmit two symbols at a time? Right. So what do I mean by transmitting two symbols at a time? So let me make this clearer. So when I want to transmit two symbols at a time, it basically means that I'm going to set, suppose in this case, oops. In this case, I have E, F, I, J, and L, right? So let me just write them down. Okay, so that I, J, and L could be confused amongst each other when sent over a channel, and E and F could be confused among each other. So I chose one from each. Okay, but now suppose I send two bits at a time or two symbols at a time. That is every message. So two symbols pasted together. Now each symbol by itself may be corrupted. Okay, so for instance, suppose I send EI, right, as one block, right? Then E can be corrupted, I can be corrupted. But as long as I can recover it, I should be fine, right? So the question is, if you are allowed to transmit more symbols at the same time, can you do better? And that's the key question. So instead of this graph, which is slightly more complicated, I'll go back to the conflict graph as before, right? Of the phi cycle. Maybe this is a bit more complicated to actually say. Let me check whether I have an example that I can use directly. Let me go to the phi cycle first. Yeah, that should be much easier to describe. Okay. So in the phi cycle, the conflict graph looks like the following. Right. So this is the conflict graph. So if I send A, it could be confused. So I cannot send A and B. They cannot lie. A can be confused with B or E and so on. Right. So the size of the maximum independent set here is 2. Right. But now I'm saying that, well, so let me take, say, A and C as the independent set. Right. So now clearly, if I send two symbols at a time, I should be able to send the following: AA, AC, CA, and CC. Okay. So these are messages over two symbols at a time. Okay. Such that none of these can be confused with the other. Okay. So A and C will never be confused with the other. Right. And therefore, if you send AA, it can be corrupted in some way, but the receiver can decode it. Right. Similarly, AC and AA and AC will never be confused because the second coordinate is never confused. Okay. So I hope the setting is clear. If you have any questions, please ask. Okay. So 4 messages can be sent. By using the channel twice. So, 4 distinct messages that will not be confused with each other can be sent over the channel. Okay, when you're using two symbols at a time. Okay? But actually, I claim that there is a better way. You can actually send 5 messages. And here's a set of 5 messages that can be sent. Right? And why can these 5 messages be sent? Okay, I claim that these 5 messages, when sent over the channel, will not lead to any confusion at the output end. Okay, and the reason is basically because of the following, that A and B conflict, but A and C do not conflict. So AA will never be confused with BC. Okay, and similarly, BC will never be confused with CE, and so on. Right? If you take any two pair of this, right, any two of these, there'll be at least one of the symbols that will not be confused with the other, and therefore the two messages cannot be confused. Okay. So for instance, if you take AA and DB, then the A can be confused with the B, but A will never be confused with a D because there's no edge between A and D. So the two messages are not confusing the receiving end. So I hope this thing is clear what I'm saying. We'll formalize this in a moment and say, okay, that V is similar to W if V equal to W or VW is in E. Okay, so similar means it may lead to this. And what we are looking for is a similarity free dictionary on G. Okay, I'm calling it a dictionary because it's a collection of words. Right? Okay, so a similarity free dictionary is all of which are pairwise dissimilar. Or in other words, it's just the maximum independence. That's all. So what I hope to do in the next half an hour is to basically look at this idea of sending multiple symbols across and formalize what is called the Shannon capacity of a graph. Okay, and we'll work towards that. Good. So now that I've defined what is similarity on a graph G, let me look at the graph which I call G power K. Just give me a minute. I'll just grab some water and okay. So based on the previous notion of similarity, let me define the graph G power K, which is basically the vertices of the graph G power K are K tuples of the original vertices. Okay, and say the edges E, and I will define what the edges E are. So if you take two vertices here, say, let me call it V1 to Vk, and V1 prime to Vk prime. Okay, so these are two k tuples of vertices. Okay, and I call that they are similar, or there's an edge between the two. If, and can someone think of what is the condition I'll put for an edge between two tuples here? Basically, they have a chance of being confused if all the k coordinates are similar to each other, right? So if V1 is similar to V1 prime, V2 is similar to V2 prime, and Vk is similar to Vk prime, then they have a chance of being confused, and then they form an edge in this graph Gk, right? If there's even one coordinate where these two will not be confused, then they are distinct, right? And they will not be confused with each other on the output. So you put a conflict over there. If for all I is 1 to k, V1 is similar to V1 prime. Let me write it in words. Oh, for all I should write this as I. Okay. So is this definition clear? So what would be the vertices of the phi cycle squared, right? So I had A, B, C, D, E on the phi cycle. Right? Now, this is C5, the phi cycle. If I square this, how many vertices am I going to get? I'm calling it square, but this power here. So the words are going to be length k words. So I'm going to have all possible combination like AA, AB, AC, and so on. So 5 into 5. So I'll have 25 vertices, correct? I'm not going to draw out all of them. But suppose I have something like CD, and I'll just draw out some of them for illustration. Right? Now, amongst these vertices that I've drawn, uh, can you label some that don't conflict with each other? Or maybe we can tell which are similar ones, right? So is AA similar to BC? Well, A is similar to B, right? But the second coordinate A is not similar to the second coordinate C. So I'll not draw. What about AA and AB? The first coordinate A is similar to the first coordinate A here, and the first coordinate A is similar to the first coordinate B. Okay. So here there'll be an edge over here. What about AB and AC? Is there going to be an edge or not between them? So the first coordinate is similar, A
Yes.
is similar to A, and B is also
Similar.
similar to C. Yes. So there will be an edge here. What about AC and CC? No edge, right? Because the first coordinate A is not similar to the first coordinate C in the second vertex. Okay. Similarly, there's no edge between AC and CD. What about BC and AC? There is an edge over here, right? Because A is similar to B and C is similar to C. BC and AB, again, B is similar to A, C is similar to B. So there will be an edge here, no edge here. Okay, so amongst the vertices that I've shown here, these are the edges that are present. I hope I haven't missed any. Yeah. Right. So you can actually enumerate all the vertices that are going to be there over here, right? One after all the edges that are there based on this. Okay, so just remember this notion of similarity, and from now on we'll work with just this, and I'll try to motivate the definition of Shannon capacity based on this. So now for C5, what you saw is that if you look at the graph C5 squared, right? I gave you an explicit example. So what we're looking at is, of course, independent sets in these graphs, right? So
Professor,
for a one channel use, yes, question.
can you explain the edge AB and BC once again?
Right. So if you look at this coordinate, they are ordered tuples, right? So if you look at the vertex AB and the vertex BC, right? A and B have a conflict in the base graph, and B and C have a conflict in the base graph. Okay, that is, they are similar. And therefore, in this, let me call it, for lack of a better word currently, two-powered or two-lifted graph, you will have an edge between these two vertices. Okay, is that clear?
Yes.
Okay.
And ACCC?
AC and CC will not have, because A is not similar to C, right?
Okay, there is no edge.
There's no edge between A and C, so there's no edge between AC and CC.
Okay.
So you can think of basically doing this K times, right? And you could think of, what's happening if you power this 3 times. I'll call it C5 cube, right? Then you'll have 5 cube vertices, okay, 125 vertices, and you can draw similar graph there. Okay. So why are we considering these graph powers? Okay, if you think for a moment, right? If you had an independent set AC in the base graph of size 2, I claim that you can surely find an independent set of size 2 squared in the squared graph. Can someone tell me why? There is an independent set of size at least 4 here. So why should this be the case? Why does independent set of size 2 here lead to independent set of size at least 4 in the higher graph?
All the combinations of this independent set could also be independent because they will.
Exactly. Wonderful. So if you take a independent set here, for instance, suppose I take, say, B and E here. I've been doing A and C. So let me take B and E in the base graph, C5. So this is an independent set in the base graph. Now suppose I take BE Cartesian product with BE, right? I claim that this is an independent set in the squared graph. Why? Because what will I end up with? I'll end up with these 4, and you'll find that no 2 of these have an edge between them, okay, in the squared graph. Okay. And you can do this for all kth powers, right? I've defined g to the power k for a general k over here, right? And you could just do the same operation. And if your base independent set size is 2, what about alpha of C5 cubed, right? You should expect to get an independent set of size at least 2 cubed, which is 8 in that graph. Just take an independent set here and take a 3-wise Cartesian product, right? Good. But what you have seen in the previous one is actually that in this graph, there is an independent set of size greater than 4, right? So that's what we saw previously. I just enumerated it out here on the previous slide. Here's 5 explicit kind of vertices which form an independent set in C5 squared. Right? AA, BC, CE, DB, and DD. So you have 5 vertices, which is larger than just 2 squared. And this is where the gain seems to come in, right? So I could just, whatever I could transmit in the base graph, in the square graph, I could transmit square of that. Okay, but actually it turns out that I can possibly transmit more than square. Okay, there are more set of two symbols at a time than just square of the original one. Okay, so keep this in mind. Okay, I hope this is clear. Okay, so the main one of the properties that I want to show is the following, that if you take the k plus lth power of some graph G, okay, the independent set, I'm sorry, this should be the other way around. So G is a graph, right? G to the k is a graph, G to the L is a graph, and G to the k plus L is a third graph, right? And just generalizing the previous one as it is, what we did before for 1 to 2, it should be intuitive that you can, given an independent set for gk and gl, you should be able to construct an independent set for g to the k plus l. Okay. So you take an independent set here, take an independent set here, take their Cartesian product. Okay, it will give you an independent set because the vertex set here is v to the k plus l. The vertex set here is v to the k. The vertex set here is v raised to l, right? L tuples, k tuples, and k plus l tuples. If you take an independent set, well, let me not write it because writing out will introduce notation that is possibly more confusing than the actual thing. Take an independent set here, S1, take the Cartesian product with the independent set S2. Let me call it T. And it will give you an independent set over here of size S times T. So I would say S times T is an independent set A plus C. Okay, exactly the same process, just generalized to more general powers. And why is alpha to the alpha of G to the K plus L greater than equal to? Because given independent sets here, I have given you an independent set over here, right, in G to the K plus L with size exactly equal to the product, but the actual independent set that is present, the maximum independent set, can be larger. Okay, and we saw that is the case when you go to alpha of C pi squared. Okay, so is this okay? I hope things are fine till now, and this idea of powers and similarity is clear. Okay, so that's going to be the basis of what we do. Okay, so I'll skip the formal proof of this. And what we had seen in C5, I've already given the example of C5, where the maximum independent set in C5 squared is strictly larger because this is equal to 5 and this is equal to 2. Okay. So that inequality need not be tight. Good. So now let's go on to let's go on to define Shannon capacity, and we'll stop hopefully by motivating what is this Shannon capacity. Okay. So the Shannon capacity basically asks the following, right? For what power k, do I have a definition here? Yeah. Okay. So suppose you take a base graph G. Okay. In computer science, it's natural to think of binary encodings as a measure of information that is contained in a string, right? So suppose I'm transmitting one of 4 strings, right? Then it can be encoded using 2 bits, which is log to the base 2. Okay. And similarly, therefore, if I'm transmitting one of alpha of G messages, right? So G is my base conflict graph. And I decided that, well, on the particular channel that I have that creates this conflict, I can send an independent set, which currently may be looking something like this and this. Right? So that's 2. Right? So that's 1 bit of information that is sent. Okay. In case you're not clear why this is 1 bit, you can forget about it. You can just take it as a definition. You will not really need this quantity too much, the log to the base 2. It's just to motivate why the word capacity came in when Shannon defined it. Okay, so bits of information transmitted is log of whatever the number of messages it is possible to transmit without any confusion. Okay, So now, suppose you have k letter words. Okay. Then what is the average information per bit? Okay. So if you're taking a base graph G, powering it multiple times, so k times, and then transmitting symbols from that graph, which, as we had seen, alpha of G power k is greater than alpha of G to the power k, right? So if you're transmitting from that, then what is the amount? So for k letter words, we are going to use the graph G power k, right? And if you're using the graph G power k, you are transmitting alpha of G power k is number of possible distinct messages we can transmit. Without confusion. Okay, that is they are basically non-similar messages. They have no chance of being confused at the output end. So if for k letter words, you are transmitting alpha G power k, which is greater than equal to alpha of G to the power k. So it looks, oh, great, I'm getting a lot of gain by using the powered graph and transmitting. I can transmit more messages. But wait, you're paying for it, right? It's not that you're getting this for free. Um, if you're transmitting one symbol per transmission and to encode messages for the base just k equal to 1, here what we are basically doing is we are transmitting multiple symbols. Right? We're transmitting k symbols to encode a message. Right? And therefore, let me call it per symbol. Okay. For k letter words, the average information that is transmitted per symbol, and this is the important measure, is going to be what? Well, the total information transmitted per message is log of alpha of G to the power k. But I'm using k symbols. So per symbol, I'm using only 1 over k. Right? So for instance, suppose I'm consider alpha C5 squared, right? What am I doing? I'm using two symbols at a time to transmit. Right? So I get log of alpha of G squared, C5 squared, divided by 2. Right? So the average information per symbol that is required is called the Shannon capacity. Okay, what is the maximum that I can do this? Okay, but notice that this is dependent upon k, right? So for instance, for C5 being the base conflict graph, what we got for k equal to 1, I got 1 over 1 times log 2. Right? So you're transferring only two messages, so log 2. For k equal to 2 though, what we got? 1 over 2 into log of 5, right? Because this was alpha of C5 squared. So by using two symbols, the average information that I'm transmitting per symbol is suddenly higher, because if you notice, this is greater than 1. This will be approximately 1.161 if you work it out or something. Okay. So as computer scientists or as in information theory, people are typically interested in this. How efficient is your transmission? That is per symbol or per use of the channel. Notice that if I'm transmitting from C5 squared, I'm using the channel twice per message. But if you're using a per use, how much information I'll be able to get across, how much useful information I'm going to get across to the output. This quantity is a measure of that. Okay, and this is the quantity that we look to optimize. Okay, 1 over k log of alpha G power k. Okay. So that's what this is. And now, because I can use the channel multiple times, I give you freedom. Okay, use it any k times, but use the k that is most optimal. Okay, so Shannon capacity, sigma of G is called the Shannon capacity. And it is the supremum 1 over k log of alpha of G power k. That is the maximum independence set. This is again is size of max set in G power k. Okay.
Sir, what is the motivation behind this definition?
Yeah, so the motivation is exactly this, right? I allow you to use the channel multiple times for a single message. Like you are transmitting, for instance, in C5 squared, when you're using the channel twice to transmit a single message. Okay. But now what I'm going to count is not the total information that is possibly transmitted, right? Without confusion, but the total information per channel use. Okay, or per symbol of transmission. So for instance, if you look at this, right, let me write out the C5 confusion example again, which is BC, CE, DB, and ED, right? So these are the 5 different messages that I can transmit by using the channel twice, right? For the C5 graph on with the vertices label A, B, C, D. That's the convention I've been using. Right? So this means that if I want to send message number 1, I'm going to send A. If I want to send message number 2, I'll send BC, message number 3, message number 4, message number 5, right? And if the output person receives some output, right? The person at the other end receives some output, he can clearly point out that, look, it was message number 1 that got to me. Okay, or I'm supposed to receive message number 2, even though B and C might individually be corrupted in the way given by C5. Right? He can point to, he'll never receive a message and be confused whether it is 1 or 2. Right? He'll be exactly able to say what is the message that was sent to him. Right? So in this case, I'm able to transmit 5 distinct messages. One of 5 distinct messages can be transmitted with 2 channel uses, right? With 2 symbols, let me call it. Let me not use channel use if that's confusing. With 2 symbols, which means each of these symbols on average is carrying an information content of log of the total number of messages to the base 2 divided by k. Okay, so this is the information content per symbol over here. So this is the motivation. We are interested in per channel use, how much information I'm able to get across on average. Now, no one is restricting you from using a larger k. Maybe if you use k equal to 3, you could get more than 1.161. Right? But we are not really stopping you from doing that, except that it may not really be useful. Maybe it's useful, maybe it's not. We don't know. Okay. So the Shannon capacity is defined to be the maximum that information you can get across per symbol. Okay. So suppose you want to come up with a encoding scheme that you could try k equal to 1. So given a base graph C5, I will power it once, you like take the second power, it's C5 squared. Look at what is alpha of C5 squared, do this 1 over k, and okay, fine, this is efficient. What about cubed? What about fourth power? Is it more efficient than second power or third power? Right? That's the question we are asking. Okay. So is it somewhat clear?
Yes, sir.
Okay, so is sending 2 symbols at a time more efficient than sending just 1 symbol? Is sending 3 symbols even more efficient? And it's not an obvious thing, right? It's not obvious that sending 3 symbols is more efficient than sending 2 symbols, but we can have some properties about it. Okay, first of all, that k equal to 1 need not always be the best. That's what our C5 confusion graph showed. But more importantly, here's a simple property that sigma of g is bounded. Okay, why is it bounded? Well, because the independent set in a graph is at most the total number of vertices in the graph, right? And in g power k, you have size of v to the power k, the number of k tuples. It's at most v power k. So sigma of g is bounded by v. So this implies the Shannon capacity as defined is less than or equal to mod v. Like because I take log of this, I get, let me write it more explicitly. It's always bounded by log of, it's always to the base 2. This is quite natural in CS if you're not used to it. So it's always bounded, upper bounded by log b. Okay. And secondly, although individual for k equal to 2, the efficiency may increase, for k equal to 3, it may drop, and so on. The limit criterion basically states that you can show the following, that it does tend. Okay, that in the limit, as you go k to infinity, you will approach sigma of g. Okay. So you can prove this just by the same superadditivity of alpha that we had seen before, right? So you can use that to get this, okay, sequence convergence. Let me not do that here for want of time. Okay.
Sir, it is possible to compute g to the power k for large k.
No, so exactly. So it's not possible to compute g to the power k also, because it has, if as I increase k, the vertices blow up, right? So even on modest graphs, computing alpha of g is hard. Then you have alpha of g to the power k, which you want in order to plug into sigma of g. So you can guess already that computing Shannon capacity doesn't seem like a easy thing. Okay. And you're right in that respect. In fact, Shannon himself said that it's really hard to analyze when he introduced this in 1956. He said that it's notoriously hard to compute even for simple graphs. Okay. In fact, the C5 example that I've taken is for a reason that, for C5, what is alpha, what is sigma of G was quite hard to know. And it was only in 1979 that Laszlo Lovasz determined sigma of C5. And he did this via very ingenious relaxation, so to say. Okay. So I'll tell you what a relaxation, and possibly the word relaxation will make sense only when we reach the third lecture. But for now, okay, so it took around these 20 years just to even determine it for C5. And in fact, even till now, sigma of G for even C7, the 7th cycle is open. Okay, and we don't know what the answer is. What is sigma of G for even C7? Okay. So it's really hard to analyze, and we don't even know how to do it. Even doing C5 was a big thing. It was really ingenious ideas were used to do it, and we'll go over how to compute sigma of C5 over the next 2 lectures. Okay, good. So I'll stop here for this lecture. I think I'm almost out of time, and maybe I'll say a couple of lines about Lovasz's approach to this. Lovasz's approach to computing the Shannon capacity of a graph goes through a certain geometric representation of the graph. Okay, you represent the graph in a geometrical setting and somehow use some property of the geometry to infer what is the Shannon capacity. The way I've said it, it seems completely unrelated. And therefore, when I even describe it, it will seem as if it has come out of thin air, slightly at least. But then many years later, it was found that actually Lovasz's approach was actually quite ahead of its time, in the sense that towards the 90s, there were algorithms defined or figured out to kind of approximate quantities in graphs. And it turned out that they share a lot with Lovasz's approach to determining sigma of G. Okay, so we'll discuss this and more in the next 3 lectures. I will stop here for now. If you have questions about what we have discussed, please feel free to ask me. Of course, subject to whatever time constraints are there.
Morning, sir.
Yeah.
Here is maximum linearly independent set is unique.
No, it need not be unique. There may be multiple maximum linearly independent sets, and you could, it doesn't matter. We are concerned with the size of any maximum.
Okay.
Maybe if I used a the somewhere before, that's my mistake. Yeah.
Mhm. So size is also not unique.
No, the size will be unique because when I say maximum, I mean it's a discrete object as a graph. So there will exist a maximum, right? So if given a
Okay.
graph there is a maximum size. Now, there may be multiple independent sets which have the same size and which may be maximum.
Okay.
For instance, you can have multiple, for instance, if you take the cycle C5, right?
Mm.
There are multiple independent sets of size 2. You could take this and this. You could take this and this, any of these.
Mm.
Or both, they are
Yes,
both independent
degrees
sets,
too.
both are of size 2.
Mm. Okay, sir. Thank you.
So the same thing can be done for directed graphs also. I mean, if you confuse A with B, but not B with A, and
Right. So a channel as defined is a directed graph, right? But when you're looking at this particular definition of confusability, I don't know of an analog in directed graphs that I can immediately motivate. Mhm.
okay, okay. And the
That
Shannon capacity is the maximum efficiency, or
yes. Yes.
okay,
So given a conflict graph is basically a description of the underlying channel, the conflicts that the channel underlying causes, right? So what we are interested in is the max efficiency of using that channel to transmit messages.
okay,
Okay. And because the Shannon capacity has a supremum, I should say the supremum is over K. K is the way, K is written here. So yeah, this is supremum over all possible K.
Okay.